All right, everyone. We have an extremely special treat this week. Professor Emery Berger is visiting from UMass Amherst. It's a huge honor, actually, to introduce Emery. I remember when I was an undergrad applying to grad school, and I got this email from him, and it was like so exciting because I'd seen he came to Purdue and gave these amazing talks, and now it's sort of really fun to invite him to our group and have him visit. So Emery's done basically everything. It's really hard to summarize his career. He's sort of the master of memory management, lots of papers on allocators, how to tolerate errors and fix errors, and how to allocate efficiently. In fact, I just learned that there's a citation to Emery in the OS 10 code base because they use his flawed allocator. But he's moved on to stuff with crowdsourcing, all kinds of amazing work in the browser, work on reproducibility, and a ton of community leadership in SIGPlan and the broader CS community. So today we're going to hear about one of these sort of broader impacts in spreadsheets.
All right. Thanks, Zach. Lovely intro. All right. So I actually have two talks that I had prepared for today. I'm going to focus on spreadsheets, but if there's time, I'll talk about this hilarious other piece of work. OK. So, but for now, let's talk about spreadsheets. So before getting too deeply into this, this is mostly joint work with my former student, Dan Barrowy, who's now faculty at Williams College, and my longtime colleague, Ben Zorn, who's at Microsoft Research. All right. So before I dig in, I want to talk to you about these two people. They're Carmen Reinhart and Ken Rogoff. They are two economists at Harvard, just down the street from where I teach, so to speak. So they wrote this book that was called "This Time is Different: 8 Centuries of Financial Folly." The book has been cited 7,000 times. And they wrote a paper, which actually was never peer-reviewed, but it's a paper called "Growth in a Time of Debt," and it's been cited almost 3,000 times. And the underlying argument that this economic analysis makes, which is the result of studying centuries of economic data, is that countries that incur too high of a debt load, that is, where their debt is high relative to their GDP, end up experiencing low economic growth. If you think about it, it's a ratio, right? There's like debt and there's GDP. It's really hard to increase your GDP, but it's really easy to decrease your debt. The lenders just stop giving you money, all right? So it works like a charm. That approach is referred to as austerity. It was, in fact, cited literally on the floor of the House by Paul Ryan as the intellectual foundation for one of his budget proposals, which did not pass because this was in the Obama era. However, it did get used also in Greece. This is a shot of the reception to this plan in Greece. Things didn't go very well, as you may know, and they weren't particularly happy with the austerity program that was imposed on them. So as you will hear later, it turns out there were some deep problems with this particular economic analysis. But you might be asking yourself, well, they did this big economic analysis with all of this data. What programming language do you think they used to do this analysis? It wasn't done manually, right? So you could think that it was C++, but this is a very simple version of their analysis. But it was not, in fact, done in C++ because C++, well, I mean, it's a fine language. It's not used by that many people. They certainly didn't use it. You might think Java. Sorry, just kidding. That's Java. So Java is more popular than C++, but only has 9 million users. No, they used the language of choice for economic analysis, Excel. So Excel, Microsoft estimates that there are 750 million users of Excel, which is 7% of the world population, which is kind of crazy. This is just Excel alone, not including Google Sheets, which is certainly another several percent of the world's population. And if you put this on a graph next to all other programming languages, it's a little embarrassing. So it is clearly by far the most popular language. And in fact, spreadsheets are this ubiquitous tool. So I mentioned that there's more than 750 million users. It is a programming language. We don't really think about it this way, but it's actually a functional reactive programming language that has this special other thing, which is data is also right there, right? So the data and the programming language live side by side. This makes it really convenient. It has a very low, very, very shallow learning curve. which makes it very attractive. It's visual. It has all of these sort of nice features. And so I have pictures of all these various domains in which it is widely used. Actually, just saw some Twitter discussion where they were talking about political science and blah, 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 and everything is in Excel, right? So why is everything in Excel? It's in Excel because it's easy, right? So people can just type stuff in. They can get charts. They don't have to go and open up an IDE or a command line or anything. It's all there, and they know how to use it. So it's used in all kinds of domains where it is actually really important. Like it's used to make these decisions, like should we destroy the economy of Greece? But it's easy to make mistakes. So it turns out there were a number of flaws in this analysis when eventually it was discovered what was going on. So this is a Paul Krugman piece, and he asks the question, so did an Excel coding error destroy the economies of the Western world? And the answer is no. Multiple Excel coding errors destroyed the economies of the Western world. So there are many errors in the spreadsheets, and it turns out that some colleagues of mine at UMass, unbeknownst to me, in the economics department, had obtained the spreadsheet and then spent a year analyzing the spreadsheet to see what had gone on with this spreadsheet. It turns out it's pretty big. And then they fixed all the problems with the spreadsheet. And when they fixed the problems, it actually inverted the findings. So the original findings were that when you enter this regime of 90% plus debt to GDP, they said, oh, your economy starts to decline. But in fact, when you fix it, it's 2.2% increase. So it suggests that actually maybe it's just fine to have a high debt load. I guess we'll see very soon in this country. So anyway, we have these people spent a year analyzing this thing, and you might think, well, Jesus, that's the state of the art. Like, surely there's something. So this is an article which actually this is from I think The Guardian, after talking about all of these issues with this spreadsheet and whatever. And they say, unfortunately, every formula is unique and has a specific task. There isn't an automated tool. Still, there's some steps you can take to prevent most errors from happening. And if you're a programmer, you immediately are thinking, yes, indeed, testing, assertions, debugger, or visually inspecting and double checking things, right? So that's kind of the state of the art, which is not great. So if you think of like, I need to debug my program, let me look it over line by line. That's where we are. So, so this is actually a screenshot of the spreadsheet. I have the spreadsheet in all of its glory here if you'd like to see it later. It's pretty big. So it has economic data for 20 countries. In the case of the United States, dating back to 1791. So it's just rows and rows and rows of stuff. There's thousands of cells and hundreds of formulas. So pretty painful to inspect every single thing. This is also a shot I grabbed from Forbes. Sorry, your spreadsheet has errors. Almost 90% do. I speculate that number is higher. I like this particular quote because it's really essentially this if you translate it into programmer speak, right? Sorry, there's no such thing as a spreadsheet debugger. Have fun, lol. That's citing myself. OK, so let me actually show you what the state of the art is for a spreadsheet debugger. This is the state of the art. This is Tom Herndon, who was a PhD student at the time at UMass Amherst in economics. He is the guy who manually audited this spreadsheet. And this is a screen cap of him on the Colbert Report. So he got something good out of it, and also a faculty position somewhere. But so he's the state of the art. There aren't that many Tom Herndons, and he's really slow. It took him a year to audit this spreadsheet. So you probably don't want to have to hire a grad student or be that grad student yourself and do this. Yeah?
Do you have a sense for how much of his analysis required domain knowledge versus Excel expertise?
That's a good question. So I would say it is, it's a tricky question. I would say it's sort of 50-50. So what we're going to get to eventually is that we have these tools that we've developed that actually find a number of the errors that they later discovered, or that they had discovered originally, I should say. And understanding some of the errors is very easy. Sometimes you look at a spreadsheet and you see one of these errors that comes out, and you look at it without any particular knowledge of the spreadsheet, as we have done for like 70 spreadsheets at this point, and you're like, that's clearly an error. Like, it's clearly wrong. Like, you read the legend, you read what it's supposed to do, and you're like, that's the wrong formula. In other cases, you see data, like it'll highlight, also we have stuff for data, and it'll say, hey, there's a problem here, and that might require more understanding. So it's a good question. All right, so Reinhardt and Rogoff went and did their analysis. I should say there's a little bit of confirmation bias. They are conservative economists. I know I'm on tape here, so I better speak judiciously. But by contrast with other fields where there's not conservative chemists and conservative computer scientists, like those things are separate. There's conservative and liberal economists, and that actually defines the kind of science you do. My fingers are getting tired. And so they are conservative economists, so they had a particular outcome that they anticipated, which is that austerity is good and that debt is bad. And UMass Amherst actually has liberal economists who do not believe these things. And so they were inclined to not believe those results and actually chase them down and found these problems. All right, so that said, clearly Reinhardt and Rogoff did not, in their mental model of the universe, think, oh, we're probably wrong, right? They thought, oh, we're probably right. And when you think you're right, you're probably not going to check to see if you were in fact wrong. On the other hand, if they had an easy tool, right, possibly they would have run it, said, let's just check to make sure. They clicked on some tool, and the tool could come back and say, you've got some problems here. They probably would have fixed them. And in some cases, I'm sure they would have fixed them. Yes?
Potentially, this means that in fields where there isn't an incentive to go nitpicking in results that you know are unlikely to be true, there might be even more errors, or errors that aren't getting caught.
Yeah, so the question is, or observation, is that in areas maybe where there's not an incentive to debunk other people, then there's probably more errors lying around. I think that this is true. Like, I agree with you. I think that there's another angle to this as well, which is that people have an analysis of something and no one cares about it. Well, if it's wrong or not, it doesn't matter, right? And so economists, like macroeconomists, have a shared body of knowledge or body of positions that they have, like that they've taken sides on. And so, if somebody says, here's some giant macro thing and it's really important, it gets 4,000 citations, probably pretty motivating to try to debunk it. If it's some sort of niche thing where it's like, the economics of minnow farming in Brunei, maybe it turns out that, you should have some particular practice and no one will care. Right? So yeah, I think that what we're basically saying is that things that matter will attract more attention and more focus. Things that don't matter, probably not so much. Yeah?
To ask the same question a different way, if you had such a tool and you could run it over spreadsheets, how much of science could you invalidate, or how many computer science professors would go to prison for accidental fraud on their grant budgets?
God. I'm not going to answer the latter. I'm not going to touch the latter question. So, I will say this. So, certainly, so we've found tons of errors, okay? Tons of errors in publicly accessible sheets. Some of these sheets are accidentally exposed on the web or deliberately exposed on the web because of some sort of transparency laws in the states. And a lot of them have errors. And there are a number of cases that we have found where when you look at the spreadsheet, you actually discover that they fudged things. This just happens all the time. So yeah, it's a concern.
Maybe Microsoft could deploy your tool, I don't know, with some nice little, it's just like a paperclip or something.
Yes, yeah. You're jumping ahead. Yeah. All right. So yeah, we'll get there. All right. So what I'm going to tell you about today is some attempts that we've been making to right this situation, to try to bring to bear what we know about programming languages to this problem, which obviously affects nearly 1 billion people. All right, so I'm going to talk about 2 projects. So one is called Checkcell. Checkcell is designed to find data errors, and I'll explain what that means. And then our latest work is called Excellent, and Excellent finds formula errors. All right, so we're attacking both sides of these problems. So first I'm going to focus on Checkcell. So you've got this big spreadsheet. What's the problem? Why is it that the spreadsheet is bad? So obviously, programs can be bad because you wrote the wrong program, right? In this case, with spreadsheets, it's a little more subtle. You have programs and you have the data. So the program could be wrong and the data could be wrong, or both. Great. All right, so lots of opportunities for problems. There's one ridiculously simple problem. This is not something that we're directly attacking, but I just want to point this out. Input errors. So empirically, people have determined, and we actually reproduced this, two decimal places, which is insane. Honestly, it's the craziest result, I think, of the whole talk. Which is, so roughly 1% of every character that people type are mistyped. And this means that 5.26% of cells are mistyped. And this guy in Hawaii, at the University of Hawaii, lucky bastard that he is, went and did some study with like a group of people, not a large group of people, and came up with this number. And we ran a much, much larger study, as I'll explain, and we got the same result, which is crazily robust. So if you think about this, though, this is like 1 out of every 20 cells that has data, if it's manually typed in, probably has an error. So this virtually means that every spreadsheet is wrong. Yes?
So does this include going back and fixing your mistakes, or is this like one pass, no backspace, like into the data?
Yeah, in this particular case, this is, I mean, I'll actually explain the experiment, but just briefly, we literally hired users to enter in numbers, to enter in data, and then we measured the kind of typos they produced. Yes?
Were the typos distributed uniformly?
No.
So do people tend to get the more significant digits right?
Good question.
Okay.
It depends.
Okay.
Yeah. Sometimes people leave off a number, especially when they're reading a long number, and they'll leave off a digit, or they'll add another digit, and then change the result by an order of magnitude. Which, yeah, exactly. OK. All right. And I should add, this is clearly not the only source of errors, right? This is just like a source of errors. In fact, really, spreadsheets are kind of like an error factory. There's just so many opportunities for errors. When I entered into this work, I assumed that most spreadsheets would be mostly OK, and that we would like find a few errors. And in fact, it's exactly the opposite. Every single spreadsheet we have encountered, virtually every spreadsheet that has data and formulas is wrong in some way, and often very, very wrong. All right, but it can be hard to see these errors, right? So you have this. This is the Reinhardt-Rogoff one again. It's over 100,000 cells and more than 20 sheets. And so this is actually the suggestion, like, wouldn't it be nice, not really, if you were to have Clippy back, right? And Clippy were to come up and say something useful with respect to the spreadsheet that you're working on, like this particular suggestion. So why is this hard, right? With words, it's kind of easy. Like, there's a limited dictionary. You can be like, oh, this word is misspelled, right? There's an oracle. But in spreadsheets, it's not like there's a separate spec, right? Nobody is like, and I believe, this should be this and whatever, and there's some logical. No, there's nothing. There's no assertions. There's no specifications. There's no tests. There's no nothing, right? It's just like, here's the program and here's the data. Go. With the data itself, it's not like, oh, just assume the data is normal. Why would you make that assumption, right? There's no good reason to make any such assumption about data, right? Especially when it comes to like money. Money is rarely normally distributed, as grad students well know. So you can't use things like outlier analysis. All the sort of tools that have been built to analyze data just don't work, right? So if you knew these distributions a priori, then they would work great. But if you see a number, like, how do you know it's wrong, right? So this is a problem. So Checkcell, the key insight of Checkcell is to actually examine the data by looking at the interaction between the data and the formulas that consume them. All right? So what it does, it can't actually know whether something is right or wrong. But what it can do is actually identify cells that have an unusually high effect on the results of the computations that are performed on them. So that doesn't mean that they're wrong, right? But it does mean one of two things. And this actually goes back to what Pavel was asking, right? Either it's important and you better make sure it's right, or it's wrong, right? And if it's wrong and it's not important, then we don't care, right? So this is a good proxy for getting at the things that we care about. So for example, so this is actually a grade spreadsheet that was on the web, which is embarrassing. But anyway, I'm not going to actually go through this whole thing. Clearly difficult to know if anything is wrong here, right? Were the grades misentered? Who the hell knows? But I'm going to use a contrived example here where it's much, much simpler to look at just for the purposes of this talk. So we're going to run Checkcell. So we implemented both Checkcell and Excellent as plugins that you can install in the desktop product of Excel. The Excellent one I actually just re-implemented while at Microsoft. I'm there on sabbatical this year, by the way. it's re-implemented in JavaScript, and it runs in their Office 365 products. You can actually like plug it in yourself. OK, so here is Checkcell in action. You click Analyze. It comes up and it says, hey, 78 has some big effect. And it comes up and just says, it marks it in red, and it offers you the option of entering a corrected value. And if you correct it, and it turns out, oh, it wasn't 78, it was 87, then it'll move on and find the next most suspicious value, and so on, until it decides there's no bugs remaining. Right? So that's essentially the workflow. So it's pretty straightforward. So the question you might be asking is, how on earth does it do this? So it does some stuff that's very simple traditional program analysis, and then it does some very fun non-traditional statistical analysis, which I will explain using pictures. Do you have a question? OK. All right. So
why 87 is a better number than 78 for that?
yeah. In this particular case, it's actually in this particular spreadsheet, it flips. I'm sorry, I didn't connect that up. So this is meant to illustrate grad fail or grad pass. So in the graduate program at UMass, if you have below a B or a B+, I think, then your classes don't actually count towards your degree. So it's the moral equivalent of failing. And so that value actually, when you replace 78 with 87, it changes it to a pass. And it turns out that this value, when you actually do the analysis, has the fact that that value is there has the most impact on the spreadsheet. And this will become much clearer very soon. OK. All right. So the very first thing it does, it needs to understand the effect on formulas, so it builds a dependence graph. It turns out, by the way, that Excel has a much richer syntax than you ever imagined. It's shocking. You probably know about, like, B5 colon B10 is a range. Some of you know that you can have dollar signs in there. Probably a lot of you know that you can have separate ranges with a comma. How many people know that what happens if you say B colon B10 and then B10 colon C10 with a space between them? You're like, what? Yeah, exactly. Intersection. OK, yeah, it does the intersection. So it would just be B10. Nice. There's also array notation. There's a thing called RC notation. It's absolutely crazy. So we actually have my student Dan, again, who's now faculty, built a library called Parcel that actually parses arbitrary Excel expressions. It's a surprisingly complicated task. You would not have thought. All right, so it builds. We go and we use this tool. It builds a dependence graph. And what it gives us is it gives us inputs, right, data, and it gives us outputs. Right? So here, when we're back at our spreadsheet, like if you go and you change something that has a very small effect on the computation, like notice, oh, I should have said, 78 is by no means some statistical outlier here, right? If you use like 2 or 3 standard deviations from the mean, 78 is well within it, right? It's not like it's an outlier in that sense. But in this range, it turns out that this value is particularly important to the final result. So how do we assess this? Yeah, Renee.
So the ratios that you have the weights for the exams, that's what makes the 78 so important.
It is part of it, but it's the fact that we're going to get to in 2 seconds that if 78 and 84 were reversed, like I'm sorry, if 84 replaced 78, then the result is the same as if it was like 84-84, then it would be pass, right? If it's 78-78, it's fail, and everything is going to be pass essentially, except if 78 is there. And this is very contrived for the purposes of this discussion. Don't read too much into the spreadsheet. But anyway, yes?
Like it's not 78, it's 98. And then the correct result is 78. So it's going to...
OK, so look. So the question is, like, all right, here's a value. Is this value correct or not?
Yeah.
So we can't tell you if the value is correct. Only you can prevent forest fires, right? Only you can prevent spreadsheet fires. And the way you're going to do this is that hopefully you're not going to look over 10,000 values to find out what the problem is with the spreadsheet. You're just going to find the things that make the most difference, right? Like if I mean, I can tell you as a faculty member, right, if I inadvertently fail half of my class because I made some typo, which may or may not have happened at some point, then I would like to know that, right? I'd like to know where the problem is. And so that's what this is going to get at. So the way it's going to work is we're going to use a technique. We're actually building an algorithm that is based on this approach called the Bootstrap. So how many of you have heard of the Bootstrap? All right, I don't mean bootstrapping a compiler. All the hands go down. OK, so the Bootstrap is a so-called non-parametric technique. It's a statistical approach that was invented by Brad Efron in '79. And it's super, super cool. And it allows you to do statistical analysis using something that was considered ridiculous, essentially simulation. So in 1979, it was ridiculed because it requires many, many cycles. It's like, who would ever use this many cycles to do whatever? And it's like, well, now it takes like 0.0001 seconds to do it. All right? So what the insight about Bootstrap, and this is something that we can talk about offline, if you don't know what the population is, and you view this thing as a sample from the population, and you can't go back and get more samples from the actual population, right? You can't resample the population. What you can do is resample the samples and generate the moral equivalent of a new population to sample from, all right? And what that's going to, that has one property which is obviously clear here. The samples are clearly from the population, because these samples are from the population, and we're going to draw samples from that. By definition, they're from the population. And the way that we're going to do it is actually going to converge to the results that would have been as if you had recourse to the population itself. All right, so let me show you how this works. So suppose we have a range. And for simplicity, I'm just grouping everything into one range and not talking about weights here. But this all works in general. You have a black box function f, which computes some value. For statisticians in the crowd, it computes a statistic. And currently, it computes fail. All right? So what we're going to do is we're going to actually draw a new sample from this population by randomly sampling with replacement from the original. So we get a population of a sample of exactly the same size, consisting of things that came from the original. And we can do this over and over and over again, right? And then we can observe what the results are out the other side of this function. So this gives us, if we do this, say, 1,000, 2,000 times, we'll get a graph. And this corresponds to what the sort of distribution should be of passing grades and failing grades. So it looks like in something like 60% of the chance of the samples, you get a pass, 40% you get a fail. All right? Yes?
Bootstrapping take into account like nearby cell values, such as exam versus homework?
No. So the way that we do this is that we rely on the fact that Excel has these ranges, and the ranges have to be homogeneous. So we only interchange things within a fixed range. So if you had, so in the case, I'm showing this in a simplified way, if I had exams aggregated and then quizzes and then homeworks, then I could only sample exams and only resample quizzes and only resample homework. And we would do that. That's exactly what we do. So we do everything. You get this world of all of these things, and this is for all of the possible outputs, right? These are all the outputs. Now what we're going to do is we're going to isolate the outputs based on which cell we are looking at, all right? So I'm going to, for example, say only the outputs that include 78. Some of those resamples will not include 78 because we're randomly choosing, right? And when we have 78, we observe, whoa, that's a very different story. It turns out that most of the time the distribution is very different. Yes?
When you say outputs on 78, do you mean 78 was in the resample?
Yeah, so here, in fact, what I meant to say was, let me get back to this graph. Here, this is all of the outputs, and then these are all the outputs without 78.
Oh, without?
Yes. Yeah, this is where the samples don't contain 78. So I misspoke. All right? So you can easily go through all of the samples and partition them, which is what we do. We partition them all the ones that contain the first cell, that don't contain the first one, don't contain the second, don't contain the third, don't contain the fourth. And then we compare their distributions to the distribution with everything. All right? And then we run a straightforward statistical test. We say, what is the likelihood of observing this under the null hypothesis? And if it is below 0.05, then we say, OK, this is not the result of random chance. We conclude that this is unusual. Yes?
So you mean exclude 78 in its original cell or in the
Yeah. No. So I have the sort of oracle, which is this is the original sample.
Yeah.
All right? And then I construct the bootstrap. And I do the bootstrap, and the bootstrap allows me to observe what would have happened if I had randomly sampled from the population and 78 just hadn't been included, which is going to happen. right? Some like 1 over e times or something. Yes.
So I'm trying to figure out sort of intuitively what this is doing. So tell me if I'm understanding this correctly.
Sure.
You basically think about the set of values you have in your spreadsheet. Each one kind of gives you additional information about the population of values out there, right? The population distribution, which is what you're simulating with the Bootstrap.
Yeah, that's right.
So when you talk about what is the effect of excluding something, you're kind of asking, did sampling 78 from the underlying distribution significantly change my understanding of what that underlying distribution is like?
Yes, that's a great way of phrasing.
Right. So it's almost like a null hypothesis test.
Yeah, that's
between I saw the 78 and I never saw the 78.
Right. Right.
Yeah, you split based on conditioned on I saw it. I didn't do
that's
it.
exactly right.
Those distributions different from the.
Yep. So we actually, it turns out, can handle not just numbers here, but we can handle strings. We can handle all kinds of things. It's actually Bootstrap is super general procedure. It doesn't have very many requirements. And the one requirement that it has is a thing called exchangeability, where you can actually change things around. And it turns out that's definitionally required by the way ranges work in Excel. Yes?
How do you sample like a table with both rows and columns instead of a one-dimensional array?
So if it is, so the answer to the question is whenever we have a range, that we can sample from the range, because the range is always treated homogeneously. So if I said, for example, equals sum A1 colon Z100, that means every single one of those things could be exchanged with anything else.
But if you had column sums and then some sort of average of the column sums, then you're only exchanging within each column.
That's exactly right.
And
And that That's right. And we only observe essentially the roots of the dependence trees. So maybe it has some effect here, but we basically build a forest of the dependence graphs, and we account for the effect that bubbles up to the top. All the intermediate results we don't care about. Yes?
Is there a way for you to infer pass and fail is an important outcome, or the user actually needs to mark pass and fail is what matters?
Oh, no. I mean, it's only because it is, it's basically because it's the root of one of these dependence forests.
You mean it's a computed value
that
isn't
That's
an
right.
intermediate for some other
That's exactly right. That's right. All right. And then we have a weighting procedure based on the size of the dependence graphs, but that's a detail. Okay? Yeah.
And I'm guessing you don't do anything clever. Like if somebody has a row sum and a column sum that intersect, you could like merge those two ranges together because you know that.
We do not do that. Yeah. We in fact, one of the nice things about this is that it's 100% generic. We don't need to know anything about the functions at all. We literally just invoke the spreadsheet recalc to do all of the Bootstrap for us. So in fact, we have a bug report in to the Excel team, which hopefully will get escalated because I sent it from Microsoft, because they, in their latest update, disabled a feature which turns off redrawing when the spreadsheet. So we have you basically do Checkcell. It says turn off redrawing, do a shit ton of computations, turn back on redrawing. Okay? And so now when you say turn off redrawing, it's like, cool, sure, does nothing. Yeah, if you're out there, Excel people, fix that, please. So it just flashes like mad, like it's some insane monkey, like numbers changing and all this stuff happening, which is very frustrating. It's best, yes.
Know you're working for them.
Yeah, that's right, exactly. It just needs some sort of warning for people with epilepsy or something. Anyway, it's very disturbing. All right, so one of the challenges of evaluating this stuff, so actually the second half of the talk, I'm going to touch on what we did. We actually manually audited 70 spreadsheets, which was a hassle. Manually auditing formulas is actually a lot easier not in the sense of it takes a lot of time, it's a hassle and all these things, but honestly, you can often look at a formula and be like, that formula is just wrong. Like it says average and it computes a sum. You're like, that's wrong, okay? That's easy. Data, not so much, right? So when we see data that's wrong, like how do we know the data is wrong? There's no way for us to know, so there's no ground truth. So we did run it on the Reinhardt-Rogoff spreadsheet, and I'll get back to that. But we also wanted to do this at scale. So what we wanted to do was come up with a procedure that was believable, that generated errors. And then we went to go see, all right, are these errors, we want to make sure they're representative, and then see how Checkcell does. So how did we do it? We went and we hired a bunch of people to make mistakes for us. which is relatively easy. So there's Mechanical Turk, which most of you are familiar with, I trust. It's an Amazon service, lets you hire people, right? And they can make money working on these hits, and then we can get their results. So here is just, for those of you who are not familiar, this is an actual page for some worker to do on Mechanical Turk. Enter the name of the product being advertised, right? So here's the actual thing you're supposed to do. You're supposed to fill in this answer. You get 10 minutes to do it, which seems maybe excessive, but fine. And when you do it, you get 6 cents, which in this case maybe seems excessive, but fine. And then, you know, the correct answer, I guess, is heroin addict hipster or something. I'm not sure what's being advertised here. Anyway, all right, so what we did is we actually took hundreds of spreadsheets, actually I think it was thousands, and extracted all of like chunks of cells and presented to the Mechanical Turk workers a PNG with the actual image, so they couldn't copy and paste it. And then they had to re-enter the data. All right, they loved this task. They loved it. They could not get enough. So there's actually, I mean, we got mails like, please post more of these tasks. There's a bulletin board kind of thing for advertising tasks. And people are like, oh my God, there's this hit from Barrowy. Go look for it. It's great. It's like, all right. So at the end, we collected 169,000 strings from these images. And we were able to use this as a generative model for typos. So we actually have a generative model for producing typos for spreadsheets. So what did we do with this error model? We then decided to compare it against the state-of-the-art tool.
The Turkers got the same reward whether they type things correctly or not.
Correct. And turns out, by the way, that their error rate was, like, remember that number I quoted? It was like 5.26%. That was the error rate we observed. I was like, come on, how could this be the case? But I don't know what to tell you.
But that number you got was independent from this.
The number that we got, so the number that we got was from this experiment. But a previous experiment had done it and gotten the same thing to the same number of decimal places, which is outrageous. I just find that. But let's all agree that 5% is good enough, right? Like 3 decimal places seems excessive.
But how did you compute that? Did you make a spreadsheet?
Who guards the guardians? Am I right? Yeah. So. There you go. That's right. We just wrote a C++ program that printed out 5.26%. It worked like a charm. All right.
C++ code doesn't ever have any bugs in it.
As far as I'm aware, yes.
If there's the same amount being paid, whether they're correct or not, wouldn't they just enter zeros or something?
Yeah. So there's so first they don't know. Second, we can talk about this at length. We actually have 2 systems for automating Mechanical Turk workloads. One's called Automan, one's called VoxPL. They're a lot of fun. It turns out that people really care about their a certain statistic, which is their long-term sort of approval rate. And this matters to them because it's used as a threshold to decide whether they can get more jobs. So they really care, way beyond 6 cents, right? They actually care relative to their viewed future income. So they're highly incentivized. You can get like spammers, as they call them, people who do like junk work. But you can easily filter them out by just saying, we want people with an approval rate of above some threshold. So that's what we did. Yes?
Were there any that you disapproved of?
So we did not automate the disapproval here. We paid every single person. Yeah. But we actually did check to see, like in a sheet, how many of them were correct. And I think we found just a couple instances of like all of them being like wrong, like you described, but very, very few, and we discarded those. So somebody made 12 cents off of the NSF's dime. I mean, something, anyway. All right, that'll be bleeped. OK, let me just move on. So we have to compare this against the state of the art, but the state of the art is a dude who was trying to get a PhD, right? Like there's literally nothing else. So we made our own straw man where we actually just said, well, pretend things come from a normal distribution, and we're going to look at numeric inputs, and we're going to look for outliers. All right? And so we'll see. Hello. This is still attached. This is still attached. OK, good. All right? So for example, if you had something that was out beyond 2 standard deviations, you'd say that's an outlier. Right? So how did we do? So we compared it to the Gaussian. Remember, the Gaussian only looks at input data and looks for outliers in the input data, whereas Checkcell takes the data and the outputs and looks for the data that has an unusually high impact. All right? So it turns out that at scale, Checkcell is correct more often. So this is a measure of total output error, like how much the actual results changed. And it turns out that Checkcell doesn't really much care about things that don't change the actual output. But the Gaussian outlier analysis does worse and worse, and Checkcell does better and better. So it has higher precision. It also has higher recall. The outliers aren't, just because an outlier is an outlier in the input doesn't mean it causes an actual impact on the result. Anyway, the effort that's required to audit a spreadsheet, that is to actually how many cells as a percentage of the spreadsheet you have to inspect to fix, also is, it's like half as many or less. Yes?
Checkcell doesn't make that assumption that the data is gaussian.
It's because of two things. So one, it doesn't make any assumptions about the data at all. And I should add, this is only numeric data. So if you had string data or other data, then Gaussian outliers, it just doesn't work at all. And then the other thing is it just focuses on the results. So if you had something, for example, where the result could be flipped, like in this case with pass and fail, right? The number is not an outlier, but it has some big result on the spreadsheet, then we will observe that. But the Gaussian outlier analysis doesn't know about it. Yes?
So your effort is higher for Checkcell. Is higher better here?
So effort as total output error increases. Is that mislabeled? I don't want to spend too much time debugging my slide, but total output error is about this. Checkcell requires little effort. I worry that this may be a mislabeling. Let me not. No, the dashes are always Checkcell, so something is amiss. I agree with you. I don't want to try to debug on the fly, but yes, that does seem confusing. Agreed. But it's fast. As a saving grace. So it is the case that in our work, it turns out that the number of cells you have to inspect to actually fix an error is in fact less. And it has a larger impact on the output in the results. We have a few outliers on all of these spreadsheets that we ran this on. In general, it takes about 10 seconds. I should add that it turns out that COM, which is the way that you talk to Microsoft products, is staggeringly slow. It's so slow, you cannot believe it. To give you a sense of how slow it is, I rewrote excellent in JavaScript. It was written in C# and F#. And when I run it in the web product, it's an order of magnitude faster because it doesn't talk to COM. So COM sucks. So a lot of this overhead that we see is actually just like COM traffic, which is crazy. Some of it is that as a spreadsheet gets very large, recalc takes some time, and we run many, many recalcs. But this is still about, like the worst case is like 100 seconds. And 100 seconds is a lot better than a year, I think. All right. So I actually, when we got Checkcell up and running, I invited one of the co-authors of this paper, this faculty member, Michael Ash, to come to our lab. And we had to, we couldn't get the Reinhardt-Rogoff spreadsheet from them. They were not allowed to redistribute it. We had to go and ask Reinhardt and Rogoff for it. And eventually they gave it to us graciously. And so we were able to analyze it, and we brought him in. And this was, that red cell over there is the highest ranked. All the other colors were from them. The red is from Checkcell. And Michael looked at it. I was like, this comes up. This is the highest ranked thing. And he looked at it, and he goes, oh, yeah, Norway. And we're like, what? So here, this is your domain knowledge thing, right? Like, do you need domain knowledge? The answer is yes. And so it turns out in this report that they did, they wrote this one extraordinary growth experience. Norway contributes fully 5.3% of the weight, even though it constitutes only 0.2% of the country years in this category. So it turns out that this has a big impact on the final analysis. And this is the most important data. It actually points to not a problem with the data being wrong, but a methodological error. That basically, it's totally crazy what they did. So there's all the different bins of debt ratio, 30%, 60%, 90%. And if a country spent 100 years in like one of those things, you just took the average, and that's fine. That's how long it was there, like 50 years. It was in this category. And what was their growth rate? It's this. What if you spent 1 year? Same. It's as if you spent 100 years. And so it turned out Norway had some weird year. Where it had a big increase in GDP, like after World War II or something. And it turned out that counts as much as like 100 years of data for other things. So it should have been normalized, and it was not normalized. So Checkcell, all in all, reported 10 errors, and they were all typos or methodological errors. And it turned out that they were ones, I think that we found a couple that Herndon et al. Had not found, and many of them that they had. Yes?
So in the case for those methodological errors, how can one look at the highlight and infer that something?
I mean, look, the person who wrote the spreadsheet, there's a creator or inheritor of a spreadsheet. All right, there's kind of two models with spreadsheets, right? So there's the person who actually authored the spreadsheet themselves, and then there's a person who got the spreadsheet from the person who left the company or whatever and inherited the spreadsheet, and then they're maintaining it, right? It's like code. So the more you know about the underlying domain, the better it is. With Checkcell, like I said, it's looking at data issues. Data issues often require domain knowledge to understand what's going on. So we found lots of problems with Checkcell in a lot of these spreadsheets, and then we couldn't say with any like 100% certitude that they were wrong. They looked bad. They seemed off, right? Like in some cases, you could see a grade that was mistyped, right? You look at it, you're like, that's probably wrong, right? Like, I don't know, it's over 100, for example. That seems maybe wrong, but maybe there's 80 points extra credit. I don't know, right? So yeah, I would definitely say that Checkcell is less immediately actionable to somebody with low knowledge than our next piece of work is that we call excellent. All right, so let me go ahead and talk about excellent a bit. We have till 1:30, correct? Okay, all right. So excellent, we just presented this work just a few months ago. It won all of these little pretty colored banners that if you've seen. We've gone crazy with these things in the ACM. We also got this banner, which was awesome. Awesome name, dude. That's not really one, just kidding. But I just wanted to stress, this is not really a linter. So we called it excellent because we could not resist calling it excellent. But linters are generally sort of heuristics and rule-based and often have very high false positive rates. But actually, the median precision and recall for excellent is 100%, which for those of you unfamiliar with precision and recall, that's as good as it gets. Just in case. So anyway, so let me tell you what the underpinnings of excellent are. Basically, we have this static analysis. So it's this static analysis, unlike Checkcell, which is kind of a dynamic analysis in a way, in that it sort of recalculates the spreadsheet. Excellent does not. But it employs this analysis which leverages the fact that spreadsheets are inherently two-dimensional. Then it uses an information theoretic approach to rank errors and their likely fixes. So let me show you what it looks like. This is actually a somewhat older version. But essentially, there's two views for the way excellent works. So there's the view where that's similar to Checkcell, and then there's this. So you click on it, and it colors your spreadsheet. And the way for you to understand this is that every different formula produces a different color, right? So if you have two different colors, it means the formulas differ in some fundamental way, which turns out to be the shape of the formula's dependent structure. And so you can immediately see, for example, like this in principle is a bunch of rectangles that you would expect to be homogeneous. Like you would expect them to all be the same color. But this is not the same color as this. This is not the same color as that. These two are different colors, right? This immediately raises questions. And in fact, every single one of those things that I just pointed to is an error. This is a real spreadsheet, OK? Then we have this other thing that actually goes and ranks the errors themselves. And it goes and figures out what it ascertains to be the biggest bug. It's essentially well, I'll explain a little more detail how that works. But it's kind of a bang for the buck. And it matches the bug, which is denoted in red, with its proposed fix, which is denoted in green. And your interpretation of this should be, you should probably change the formula that is in F6 to be like F7 through F11. All right? So it turns out that compared to previous work, the previous state of the art for formulas is this thing called custodies, which is a rule-based heuristic approach. It has vastly higher recall. So they went and visited 70 randomly selected spreadsheets from a large corpus and then used their tool to find errors. when we ran our tool on it, we found tons more errors. So we found errors that they had found, and then way, way more. And then, so this is actually the median, this is the precision. And so we have this little bottle graph. So it's hard to see, but the vast majority of the stuff is up here at the 1. So the median precision is 1. The mean is 64% versus 0 is the median precision for custodies, and a mean of 20%. So we're doing pretty well. So there are these two views that we call the global view and the proposed fixes. And it kind of allows you, the global view lets you see the whole like gestalt of the spreadsheet. And then the proposed fixes guide you through a spreadsheet, which is especially useful if you have a big spreadsheet. Let me show you a few spreadsheets because it's fun. There's so many bad spreadsheets. It's absolutely amazing. So you look at these spreadsheets and you're like, oh, this spreadsheet seems fine. Everything looks fine. It's like they're all like dying inside, but they look great. Like they're like well made up. Like everything looks clean. But then you like run the global view and you're like, what? What happened here? And so there's all these different formulas, like totally discordant. And these are all errors. So let me dive in a little bit and show you one of them. This is super awesome. So this is kind of off by 1 error of a sort. So this formula refers to these. So it's referring to the row below. Oops. And there's like, so you can see like actually some of them refer to the right row and some of them don't. So that's too bad. Does not give you the right answer, as you can imagine. Yeah, actually this particular one, this is an off by 2 error. Not an off by 1 error. You thought there were only off by 1 errors, but no, with spreadsheets, there's off by 2 errors. So here's another one. This is actually meant to be tracking particulate matter in the air. And it looks really official. It's from some state agency, I think from Washington, in fact. And then this is the global view. And you can see these colors, like why is that color in the far right-hand side different from the other colors? And it turns out that that one actually leaves off data. So these things just happen over and over again. Here's another one, some time tracking thing. And again, you turn on the global view and you can immediately see these sort of problems, like where the colors are all different. So this particular one, this one sums the data above, and then all the others sum the data below. Yeah, this again happens over and over again. So applied to this particular spreadsheet, in fact, when you run the proposed fix tool, it comes up and says this is the worst bug, and it should probably look like these other formulas. And then it goes and highlights the other formula. So it does a really good job. So how many of you have used Excel? All right, so nearly everybody. Good. Somebody is not listening. So how many of you ever noticed this thing in the upper left-hand corner of, yeah, so some of, oh, see, it's always like a small fraction. So this is Excel's built-in bug finder. And so basically it puts up this little triangle in the corner where it says, according to some rule, that something is wrong. And so as you can tell, this is clearly a false positive, because 42. But anyway, it turns out it's a false positive and false negative machine. So the median precision recall is 0. All right, so this can be seen pretty clearly because it has these rules that are just like manually curated. And a lot of the rules, like this is the best one right here. Formula's inconsistent with other formulas in the region. But it literally is like, I look up, I look down, is my formula the same as those? Yes. Don't check it. No. Check it. So if you have a total, you have some other thing like this that's it's naturally different, then it raises a false positive. A bunch of them, my favorite is one, numbers formatted as text. This happens all the time. And it's like, it doesn't matter. You can sum a number formatted as text. It does the right thing. And so we found one spreadsheet that actually chokes the web product because it puts up all those flags in some like background thread. And it was, this whole spreadsheet is just full of them. So it was catastrophic. It took 20 seconds to display the thing. Every one of them is wrong. Yes?
Can I ask a high-level question now that we're exactly, especially because of the geospatial thing?
Yeah.
I'm going to hear your answer and then I'm going to sneak up to get something. But you know, now that you've worked on this for a few years, how much of this is the copy and paste model, right? I really am supposed to copy down these formulas. Now, I, as a programmer, would be very happy to say, that these range of formulas are supposed to be the same with the row letter or row number being incremented, but I have no way to do so, and so errors creep in.
Sure. Yeah, that's a good question. I mean, I think, so, one of the problems with spreadsheets that Dan is pointing out is that you have to copy and paste things. It's very difficult to make a user-defined function. You can make them. You've been able to make them forever. It's complicated. It's hairy. There's actually work going on at MSR Cambridge on trying to do this. And it would be nice if there were some way to do this. They call them sheet formulas. There's certainly copy and paste. There's also you can drag a thing across and it copies them over. That certainly leads to lots of errors, and it has a big impact on the number of errors. I think that, though, that the biggest problem is the lack of visibility. Like when you put in a function and you type it in, then you just see the result. And you can go back and you can click on the little cell and you can see what the formula was. But when you look at the spreadsheet as a whole, you just can't see what's going on.
I see. And so, and I do that constantly because I'm a programmer. I'm constantly going back and looking at the formula.
Yeah.
But I'm interested. So in some sense, you're rediscovering spatial structure that the creator is aware of. And
that's the
error
hope.
here,
That's right.
error there, right?
Yeah, that's right.
And whether there's perhaps a way to get them to surface that and
Yeah.
specify that.
Yeah, that's right. I mean, I think that if, again, there's some sort of intent, and we're going to get to that very quickly. I'm not going to spend too much time talking about this. But we use these assumptions, and I'm going to walk through the assumptions really quickly, and I think that that's enough to characterize how this works. And the assumptions basically are that people do have some sort of intent that we can recover. And we can recover this intent, as I'll show you, and then discover these anomalies with respect to the intent in a contextual way. All right? So how does it work? At a high level, we take advantage of 3 observations. So there's 3 observations. This is exactly what you were saying, copy and paste. There's a lot of repetition. There's no user-defined functions. This is a standard part of the way spreadsheets work. All right? So if we discover, we expect these things to be reasonably consistent. The second one, users do not organize spreadsheets randomly. Well, some do, but they should not. It's really hard because when you organize spreadsheets in an irregular way, it turns out that the formulas are really a pain to write because formulas kind of push you in some sense. They nudge you, if you will, to use rectangles, right? They have a built-in rectangular syntax, right? So you say, I want a range to cover this span of rectangles. That is column, column row, colon, column row, the end, right? So most spreadsheets that actually have formulas have rectangular layouts. In fact, we measured this hypothesis, and we found that more than 90% of the spreadsheets over this huge corpus of spreadsheets have rectangular regions. All right? So it's not a surprise. No one should be surprised by this, but it turns out to be important. The third observation is that most of these errors are actually reference errors. Why do I say that? Well, you could, of course, type in average when you meant sum, or standard deviation, or something. But that's not the source of problems. The source of problems is you picked the wrong range to operate over, right? So, in fact, sum is like 75% of the formulas in spreadsheets. It's like sum is everything. And then people do manual composition of things, and then there's a couple others, and then there's a long tail. So it's mostly about the references.
On references, the things I found most tricky in spreadsheets are VLOOKUPs and indirects.
Yeah.
Do people use those a lot, or?
Yeah.
Okay. And
VLOOKUPs in particular.
Okay.
Yeah. So sum is by far the most common, and then VLOOKUP is the next. And then everything else is like noise, more or less. So in sum, spreadsheets have layouts. Formulas are repetitive, and they're organized rectangularly. Great. So what Excellent does is it looks for surprising deviations in those structures. All right? So the hypothesis is that irregularity indicates errors. Now, of course, like that, the guy before when I showed you this, like that number 21 is clearly an outlier, right? But not here, right? And so as long as all the tall people stay far away from me, then everything is good. And so you need to consider the context. You can't just be like, oh, this is a tall one. No, it's about the rectangular regions. So we're going to basically group things into rectangular regions and look for disruptions in the rectangular regions. All right? So that's how the context happens. So once we have the context, we can ask this question, is this cell surprising in some way? And then if we color everything differently based on something about the structure of these spreadsheets, whoops, jump the gun, then you can say, you can measure sort of how surprising that is. All right. So what do we mean by surprising? It turns out that we're appealing to Shannon and information theory as a proxy for irregularity, right? So this is surprisal. So regularity is low entropy, disorder is high entropy. We want to measure the entropy of a spreadsheet. How are we going to do that? We need two things. We need something we can count, so we can plug it into Shannon's formula. And then we need a procedure for inferring the intended rectangles. So I'm going to, luckily this is all animation, so it'll be very quick and easy to understand. How do we count? You can't just count ASTs, that would be a little weird. What we do instead is we actually translate all of the references in a spreadsheet to literal 2D Cartesian vectors, right? So we essentially can capture the spatial relationship and the dependence relationship of cells to other cells. So this is a nice way to like capture both at one fell swoop. We actually can, yeah?
You're going to ignore the fact that it's sum, and you just
Yeah, so we actually have a way. So if you generalize this, you can actually add more features to the vector if you want. And still, I mean, it's weird to be a metric in this way, but we want to preserve its metric properties. So actually, if you did sum or something like this, you would want it to be one-hot encoded. So you'd have sum as a 1 and everything else is 0, and this is a 1. So the distances were not artificially skewed by like sum is 1 and average is 2, and that doesn't make sense. But yeah, this is general enough to actually handle that. But in our default case, to answer your question directly, we ignore it. We just ignore the title of the function. And in fact, if you say, this is nice because if you wrote B10 plus B11 plus B12 plus A10, then we will also treat it exactly the same as if you'd written the sum. And if you did it in a different order in the ranges, we'll treat it exactly the same way. So it could have a false positive, where it rules two things as being the same, but it never has a false negative. Because if you depend on different things, you're a different formula. All right, so vectors turn out to be position independent. We have a way of capturing these absolute references as well, which I'm not going to talk about. But basically, if there are two formulas that compute the same thing, they have to have the same vector sets, because those are their dependencies. That's the exhaustive list of their dependencies. So we don't count a set of vectors. We instead compute the resultant vector, and we call that the fingerprint. And we take the norm of it, and then we can count how many occurrences there are, right? So that gives us something we can count. This is really fast, so we can actually measure equivalence of two things by just comparing two numbers, which makes this very, very tractable and very efficient. So now we need to infer intended rectangles. So like I said, our working assumption is that users are not insane. So we're looking for layouts that minimize entropy. So this example, I'll just show you how this works. Here's an example that has two non-obvious errors. So this is one of them. This is another one. When you go ahead and you compute all of these, what we call fingerprint vectors, which we then use a norm on, we get these results, which you could translate to colors. I should add data strings and white space also can have fingerprints, so it's not just limited to formulas. And then we go and we do a decomposition of the spreadsheet. We look for rectangles that minimize the sum of the entropy, and then we rinse and repeat. So this looks like this, right? So you say, oh, here's one decomposition. So we're basically looking for rectangles. Here's another. I should add, I love this, this animation, so I didn't get rid of it, but I recently came up with a more efficient way of doing this that avoids this. But anyway, it's so pretty. Dan put so much effort into doing this animation. I had to do it. All right. So anyway, it basically does this decomposition, and you get the entropy of the spreadsheet, like this nice rectangular decomposition. And then if you were to just take that picture I showed you a second ago and map it onto colors, that's the global view, and we're done. All right, here's rectangles, and here's their colors. However, if we want to actually like find things that are surprising, what we do is we actually look for every pair of rectangles that when you merge them become a rectangle again. And that's a potential fix. So this is not a potential fix, that red, right? Because it doesn't merge a rectangle. We assume that the user always intended to create rectangles, right? Here, however, we say, oh, these two things could be merged and form a rectangle, so those are potential fixes. Then you take all of the potential fixes, and then you mimic the effect of actually fixing them. That is, you transform the fingerprints. So we alter them so they have the same actual value. And then you can measure the entropy of the spreadsheet after you apply this fix. So you simulate the effect of applying the fixes, and then you rank them in this way. We also measure how much you have to change one formula to match the other formulas. So I'm not going to talk about that right now. But it basically means that if you have something that's a near miss, it's much more likely to be a fix than something that's a totally different crazy formula. So this avoids, like, I have a grand total. And it's like, I would like the grand total to be just like all the other sums. It will probably not do that. Mike?
What's the definition of entropy?
So the definition, it's literally the entropy from Shannon's definition. So it's essentially, if you have, it's the amount of information that you get negated by, and logged and all this stuff by splitting things off, yeah.
The surprise
Yeah.
is observed.
Yeah, that's right.
And this is across the entire spreadsheet.
Yes, yes, exactly. And across the entire worksheet, which means the one page of a spreadsheet. Yeah. Okay. All right. Great. So just about out of time. Perfect. So just to sum up, excellent works. You can actually run it. We ran it on 70 spreadsheets. I found lots of errors. It's very precise. Just to circle back to the Reinhardt-Rogoff spreadsheet, we applied excellent to the Reinhardt-Rogoff spreadsheet as well because, you know, who can resist? And in fact, it immediately flags the top 2 bugs that were cited by Herndon et al., which is great. And it's actually pretty cool. So the red bit is the surprising formula. And the funny part here, and this happens a lot, more than you would hope, these are the 20 countries that they analyze mysteriously in reverse alphabetical order from US to Australia. And you're like, oh, that seems fine. And then all the ones that are supposedly correct, because they're the majority, are all wrong. They all systematically excluded 5 countries, Denmark through Australia. And when you do the global view, this kind of jumps out at you. You can see that this formula is actually, I've got it a little off the page. Damn. But this formula is different from these other formulas, and the reason is that it doesn't actually include that data. And this has a huge impact on the spreadsheet. As you might imagine, leaving off 5 rich countries with high debt loads turned out to actually right there negate the results when you fix that bug. And then it just gets worse and worse for them. Anyway, that's it. So this is my awesome logo for my research group. I actually have coasters that I meant to bring. I'll have them in my office here later, not today. And you can go to excellent.org and download the plugin if you want. And sometime shortly, I hope to have the thing up for working in Office 365. Super easy to add an add-in, by the way. It's insane that they make it so easy. Like, you're like, well, who is this company? It literally comes up. You like click insert. It says add-ins, and it has a link in the right-hand corner. Upload your own, and it's like for developers. You're like, click, and you click on it, and then it's installed, and that's it. Yeah, it's pretty awesome. Anyway, yes.
Nice talk. Thank you.
Thanks.
Very entertaining, interesting stuff. I was just curious. I might have missed it, but for excellent, when you're evaluating, you know, sort of the balanced accuracy of your filters, how do you know what ground truth is? You're operating on spreadsheets that came off the net that you suspect have errors?
Yeah, right. Good question. Right. So, so the people who did Custodies had manually curated 70 spreadsheets. They used their tool. And they went and found errors. Okay. We obtained the Custodies tool, and we've then looked over all these things. There were a number of errors that they came up with that we actually felt are not unequivocally errors. But we included them anyways in their count to say, OK, this is recall for you, fine. And we consider it a precision as well. But then our tool revealed tons of errors. And the way that we adjudicated these errors is it was pretty conservative. So all 3 of the authors had to agree that it was unequivocally an error. There was no room for discussion that this was an error. And this would be like, here is the exact same legend, right? Here's the exact, like we needed to understand the semantics of the spreadsheet. So there were some cases where the spreadsheet was in language that we did not know, where we're like, I don't know. Like there was something written entirely in Tamil. I was like, I guess I could have asked a colleague. But we essentially just went through and said, we don't know what the story is with this spreadsheet. So it really looks wrong, but we're going to ignore it. So we were pretty conservative. Oh, no, so that was our oracle. So basically, when we went and found things, we found all of these bugs. So the bugs that Excellent found they could be false positives, right? So it comes up, and it's like, well, is this really a bug? If we decide it's not a bug, then it would be a false positive.
I see, but not unequivocally a bug.
It had to unequivocally be a bug for us to consider it a true positive.
Oh, Otherwise, you count it as a false positive.
That's correct.
Okay, as
Yeah.
opposed to just eliminating it from your data set because you don't know.
No. We were as conservative as possible.
So you spent hours and hours and
Yes.
hours analyzing other people's
Yes.
broken
Yes, we did.
spreadsheets. That is dedication.
Yes.
So all this work assumes like the presence of good actors, right? Like you'll just have few errors here and there, but you also mentioned
that's not actually true.
Okay.
Yeah.
Well, so
so we do not assume that there's a low error rate. When we entered into this work, we assumed that we were going to be looking for rare cases, and we determined this is absolutely not true. So this is a advertisement for another talk that I was going to give. But anyway, but like this particular spreadsheet, it's just nothing but errors. Like, I mean, it's tons of errors. So we originally were like, let's have a threshold of how many errors we find, and that will be how we cut things off. It was like, nope, you cannot do that. Yeah, because there's so many.
Yeah, sure. But I guess so say I'm an evil accountant and I've watched your talk.
Yes.
It seems that what I've learned is I should just make a ton of very small errors, right, in places where.
Oh, for the data. Well,
Yeah.
but you're trying. I mean, if you're okay, so it's an interesting question. All right, so if you're a bad actor, you're trying to change the outcome. Okay, so then we're going to find the numbers that change the outcome with Checkcell. With excellent, what we're going to find, and I didn't talk about this in the talk, we actually color data now as well. So let me make sure this actually works. Good. Okay, great. All right, so this is revealing the structure of the spreadsheet. So all the different colors are different formulas. And so like I said, these are wrong. So this one is overtime, and it's max B6 minus 40, comma 0. But you can see there's week 1, week 2, week 3, week 4, right? It should be the sum of all of them. And so these are all wrong. But then this one is also wrong. It only includes B, C, and D, but it should have included E. All right? But then we also have, like, these are in this caution yellow color. This is, like, unreferenced, I guess. Yeah. But some of these numbers, oh, yeah, this was, like, yeah, this is pretty awesome. So these are all different, right? This is different from all these others. You'd expect these all to be data, right? It makes sense, like, this is hours worked. This should all be data. But in fact, the person fudged. And so they clearly didn't have the data, and they just wrote average for all of these, right? So the only way to actually successfully evade, I would say, excellent and Checkcell is to get rid of all the formulas. Just dump the formulas and produce data, right? And then we have no recourse, right? Like excellent is all about the formulas and what it references, and Checkcell is about the data and viewing it through the sort of microscope of the formulas that use them. No formulas, there's not much we can do. That's not entirely true. We actually have an analysis that takes advantage of a thing called Benford's law, which is awesome. All of you should read about Benford's law. Go to Wikipedia, Benford's law. So we have a thing that colors the data based on its divergence from the expected distribution of the starting digits of numbers. And so that actually is used to reveal fraud. It's actually good for a variety of different processes. Sure. Yes. Where there's a, it has to do with. I mean, it's actually like subtle as to what's going on, but it's about uniformity over a log scale. Okay. And so that's something that auditors have known about for many years. We can implement this in Excellent just for fun, but that's about as good as it gets. And it's actually funny because when you do it, you can actually see like here's the budget. The budget diverges really widely from the Benford's law distribution, because the budget is totally artificial. And then the amount of money actually spent, the actual expenditures, almost exactly hews to Benford's law. And so that's good. Like if the budget is being messed with, then that would be like where are the expenditures going? And you saw that divergence, that would be something, but yeah.
Yeah, the reason I asked is specifically for the case of maybe auditing research data, right? So maybe you require that formulas actually exist, so there's some like baseline where they can't be so.
Yeah. So in fact, the Reinhardt-Rogoff, this spreadsheet was not available publicly. This is their working spreadsheet. They actually produced output spreadsheets which just had data, and then it's like something happened, right? So it's really hard to audit them. So but I mean, if somebody is trying to evade auditing, the more sophisticated they are, like the less information they give you, the worse it is, right? This is why the IRS gets to like get all of your information, right? Instead of just like, hey, here's your tax return. Yes.
So
My understanding is that Reinhardt and Berger, they stand by their conclusions, even though their spreadsheet's completely wrong.
Yes.
They still say that austerity was the right thing, and that they have stopped sharing their spreadsheets on subsequent work.
So I don't know about the latter part, which is hard to say which is more distressing. I'm aware of the former. So they wrote a response to the study that was done by my UMass colleagues, and the response was just like crazy making. It was essentially like, yes, we agree that they found these things, blah, 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 but we stand by our conclusions. Like, even though the analysis is now shown to be wrong. Yeah, as Colbert said on his show, because that's how science works. So, yeah, the spreadsheet thing, I mean, I can understand. I mean, it's the exact same thing of like, sharing your code and sharing your data in general, right? Like, if you don't want people to ever find out that there was anything wrong, right? A good way of avoiding that is security through obscurity. But it would be unfortunate. I hope that's not true.
Well, they won't get the badges.
Yeah, that's it. Yeah.
Okay, let's all thank Emery for a great talk.
All right.